Draw my physics.
So what is gravitational force? The equation for this is Fg equals big G, big M, little m over r squared. Now, this is defined as two objects which have attraction to one another, and in this case, one of the objects has a gravitational field affecting the other object. Now, in this example, radius, or r, is the center mass distances between these two objects. And again, this is radius. Other variables is big M or small m, which is defined as two different objects of masses that will be discussed later, and the big G is gravity force constant. These will be the variables for gravitational force, which will be discussed later.
How does centripetal force relate to gravitational force? So we're going to draw two planets, for example, and one is orbiting the other, and the line drawn is the centripetal force. So how are these two related? Because a planet, for example, is orbiting around one, it creates this circular-like motion, which is very similar to that of gravitational force and centripetal force. So we're allowed to say that the force of gravity, or gravitational force, is equal to centripetal force. The equation is big G, big M, small m over r squared is equal to mv squared over r. Basically, centripetal force is equal to, or always equal to, mv squared over r, which is the equation. So now we're able to create an example. So there's the sun and the earth. However, these is not drawn to scale. And there's also the space shuttle that is orbiting the earth in a circular-like motion, and the earth is also orbiting the sun in a similar fashion. For the space shuttle, it takes or requires 6 Earth years for one full orbit or rotation around the Earth. So then we can now ask the question of what is the orbital radius ratio between the Earth and the space shuttle.
Now, after deciphering these two equations, we can now solve for the orbital radius ratio. So first we start out by writing these two equations, which are gravitational force and the centripetal force. Now we can set these equal to one another as discussed earlier, and set these two subscripts, which are S, representing the sun, and SS, which is shuttle or the satellite. After doing this, we can cancel out m or little m on both sides, as they will cancel out once solved. Now, velocity is defined as 2 pi r over t, which is period, and since it's squared, for velocity, we'll just square it right away, making 4 pi squared r squared, and the radius will cancel out on both sides, as one is on the numerator and one is on the denominator. We'll now rewrite this and solve for radius. Now, we'll put the radius to the right and the other variables to the left, and then simplify these. And you'll get the radius cubed for the satellite or shuttle to be g m of the sun, period squared of the shuttle or satellite, and 4 pi r squared, or 4 pi squared. We can use the same concept except rewriting everything but changing the subscript SS and instead writing E, representing Earth, compared to the sun. Now we'll take these two radius equations and just write them out for reference in solving for later use. And again, the subscript SS is for shuttle or satellite, and the subscript E is for the sun. And keep in mind that I wrote it wrong in the beginning. Initially, these were supposed to be cubed and not squared. And now we'll just set them over one another in this solving process, as we're going to find the ratio, which means one will be on top of the other. In this case, I put the satellite, its radius, and this will be over the Earth's. Now we just write this over one another, and we notice that 4 pi squared will cancel out on both sides, and so g and big M, as they're the same value and will cancel out, leaving the period for the satellite and the period for Earth squared to be the orbital radius ratio. So now we'll take this real life example as said earlier and make 6 years of this satellite again, which orbits Earth per Earth year. Now this will be the two periods which are the orbital radius ratio, which will make 6 squared over 1 squared. Again, this is per year, which is why it's 1. And we'll simplify this so that it's 36 over 1, leaving 36 as the orbital radius ratio.
Thanks for watching. Special thanks to Mr. Albertante, our high school physics teacher.
For teaching us all that we know and all about this topic, so special thanks to him. And shout out to Lil Star, the boy, for his valiant efforts.
Yes. Thanks for watching.
Creating. Thank you. My name is Paul.
My name is Brian.
What are we going to be talking about?
Physics.
Oh shit!